C. Okay, so this is the general framework. So, so let me just remind you where mirror symmetry comes from. So mirror symmetry is based on the following idea. That there are there are pairs of Calabi-Yaos with the following property, that there's some physical theory, which I'll call Y. So you can think of this as some model of the universe or something like that. And that this physical theory is modeled by, or is described by two different descriptions. On the one hand, we can view it as a type 2B/A string theory compactified on X check. And on the other hand, we can view it as a type 2B/A/B string theory on X. Okay, so we have this physical theory Y, which is somehow an object that we want to understand. And the point is that we can view it two different ways in terms of two different string theories, right? On the one hand, some type 2A theory on X, that'll be related to some type 2B theory on the digital. So notice that I've sort of written them in backwards order so that the first letter is supposed to correspond to the first letter. Okay, so what does this tell us? Well, one of the lessons that we have is that this physical theory is going to contain a bunch of particles. Naively. Okay, and the idea is that these particles, by this sort of D-brane picture of string theory, these particles are described by D-branes in these two theories. So we have the following sort of picture. Okay, so we have a diagram. Okay, so here let me put the Calabi-Yau manifold. And here I will put the particular string theory we're considering, so type A or type B. And then these will be the objects that are supposed to describe the D-branes, which are sort of associated with sort of the same thing as the particles. Okay, so on X, type 2A string theory, then the D-branes are described by elements of this category of the symplectic structure. And same for type 2A on this guy. And then for type 2B, the D-branes are described by the derived category of coherent sheets. Okay, so by the duality then, we expect that Y are somehow objects which are defined independent of the model, right? We expect to have a relationship between the D-branes, right? This describes particles on Y, and this also describes the same set of particles in Y, right? So we should have the same, these squares should be related to one another, right? So this is one way of thinking about Kontsevich's homological mirror symmetry proposal, which I should sort of emphasize that his proposal came before this picture, before we had this sort of D-brane picture. So in some sense motivated, I think, the D-brane picture. But looking back, you can think of it in terms of this picture. So there's something which we need to pay attention to a little bit here, which is that there's going to be a lot of particles that appear in these theories described by these categories, which are in some sense not realistic. So in particular, there will be particles that you formed by jamming two electrons together or something like that. And these, of course, are not physical. And it's sort of expected that, or you expect that they will all break apart as soon as you let them go. So there's some, so for example, so some non-realistic particles. Something like a particle that you obtain by jamming two electrons together into a particle. And of course, electrons don't like to live together, so this will break up into two electrons, right? So this would be some particle which is described by an element of one of these categories, but is not a realistic particle that you would see in nature. Okay, so how do we describe the realistic particles? Well, by the sort of usual principle in physics, right, the realistic particles minimize in energy, or maybe not minimize, but yeah, say minimize some energy, some Lagrangian, right? And in particular, that means that they should solve some PDEs. Okay, so we have this sort of classical physics point of view. So, so a long-standing conjecture in the field, going back to a sort of folklore conjecture, in the field is that there should be a way to describe these realistic particles purely in terms of algebraic structure. So, or in other words, said differently, solving the PDEs should be equivalent to some algebraic notion of stability, which I will mention later in the talk. But in particular, there should be some purely algebraic notion which lives on one of these categories, which somehow predicts whether or not your object solves the relevant PDE. Okay, so that's the sort of general picture. And then there's more sort of an elaboration of this picture, which is also very important, which is that if you don't have an object which solves the PDE, right, then that means it's one of these objects which breaks up. Then actually the way that it breaks up should be related to some notion of so-called Harder-Nahr-Siemens-Shadri filtration. So there should be some relationship between the failure to solve the PDEs and algebraic geometry as well. And that's also very important. So let me try to tell you what these PDEs are. But first, I should make a disclaimer, which is that these categories are extremely complicated. There's a lot of really complicated objects in them, which are hard to understand sort of on a purely geometric level. And so what I'm going to do is just describe the equations of motion for the simplest possible particles in this, or simplest possible objects in these two categories. So that's a bit of a disclaimer. So what are the PDEs for some sort of simple objects? Okay, so right. So let me first discuss the A side. So the A side, this is sort of typically associated with symplectic geometry. So this Fukaya category is a symplectic object, and so the equations have to do with some sort of very nice symplectic objects. So here's the picture. So an element of this derived category and I'm going to assume that this element is very simple. This is just the Hamiltonian deformation class of a fixed Lagrangian. Of a Lagrangian. So in particular, we have so what does that mean? So i.e., we have a submanifold L inside of X. So this is an n-dimensional submanifold of this Clavial manifold with the property that, the symplectic form restricted to L is identically 0. So that's what it means to be Lagrangian. Okay, so so then we consider L modulo certain deformations which define this class. Okay, so now we can ask for an equation. So this equation really goes back to Harvey and Lawson in the 80s from a purely differential geometric point of view, but it turns out to be the equation for stable objects. So what's the equation? So we want to find L prime in this L. So in other words, you can think of L prime as just another embedding of this fixed Lagrangian. So such that if you take the imaginary part of the holomorphic volume form after possibly rotating by a fixed unit complex number, this is 0. Okay, so here e to the I theta hat is an element of S1 is constant. Okay, so maybe L prime. So this is a fully nonlinear PDE for an embedding of L into X with this restriction that, that L prime has to be Hamiltonian isotopic to the original embedding. So there are lots of ways to, people have tried to attack this problem of existence of special Lagrangians. And perhaps the most natural way is to attack this using the mean curvature flow. So this problem is related to understanding the long time existence and convergence and singularity formation of the mean curvature flow. Sorry? Theta hat is just a constant, yeah. So you can imagine you should integrate omega over L. That's a constant which doesn't depend on the deformation of L, and then you should rotate by that constant. Does it make sense? Yeah, yeah. So you just integrate over L of omega. And you should hopefully be able to write this as a positive number times e to the I theta hat. So then if you want this to vanish pointwise, then it should also vanish when you integrate over L. And now since that integral is independent of deformations, then you can sort of tell what it has to be by multiplying and taking imaginary parts. Make sense? Okay. Okay, so right. Okay, so so this is a PDE, which let me write out in sort of a local model for what this PDE is. So the local model here is just going to be the sort of trivial Clavial. So it's going to be Cn with coordinates zi. The trivial, or the sort of usual symplectic form. And the usual holomorphic volume form. So this is the sort of local model. So then what does it mean to be special Lagrangian? Well, we can look for special examples of these. So imagine that we're looking for, so it has to be half-dimensional. So we might as well assume that our special Lagrangian is the graph of the real plane, for example, right? So let's look at graphs. Which look like x1 up to xn go to x and y of x. Okay. So what does it mean to be special Lagrangian? Well, the first thing you observe is that imposing that it's Lagrangian implies that, in fact, this graph is just the graph of a function. So it implies that this graph has to be of the form x goes to x, and then the gradient of f of x. Locally, where f is a map from Rn to R. So here f is a map. Oops. Okay, so that's what it means to be Lagrangian. Now we impose the special Lagrangian condition. And what you get just by plugging it into this formula is that the sum from I equals 1 up to n of the arctans of the lambda i's should be a constant, which I'm going to call also theta hat. Yep. So theta hat now I'm not taking to be determined by an integral. I just want it to be constant. You can imagine this, you could still ask for solutions of this equations for any theta hat. So if this holds, then it will be special Lagrangian, where these lambda i's are the eigenvalues of the Hessian of f. Okay, so this is a fully nonlinear elliptic equation, and its solutions at least give a local model for special Lagrangians. Okay, so that's the sort of symplectic side of the story. So what about the complex side? So on the complex side, there are some, so now the category is the derived category of coherent sheaves. That's a very complicated object, or set of objects. So what we can do is isolate the sort of simplest objects, which are line bundles, for example. Complex side. So this is the so-called B model. All right, so in this case, let's look at the simple objects which correspond to line bundles over our, well, let me actually get rid of the omega, over this Calabi-Yau manifold. And in fact, more generally, we can consider line bundles supported on subvarieties, holomorphic subvarieties, where V is a holomorphic subvariety of X. Say smooth, yeah, right? Okay, so in this case, the equations of motion were computed independently by two different groups. So the first group is a group of physicists, Marino, Manasian, Moore, and Strominger. And the second group is Lung, Yao, and Zaslow. And the result is the following. So an element L, so class of a line bundle in this derived category, solves the equations of motion if the following is true. So if there exists a Hermitian metric H on L such that the curvature of H solves the following equation. So again, there's an imaginary part, e to the minus I theta hat times omega minus f. And then you take the top power is 0. So here, or more generally, take n to be the dimension of V if we're working just on V. Okay, so this is the PDE. So this is again a fully nonlinear elliptic equation for f, or for the curvature rather. It's a fully nonlinear elliptic equation for the metric H. So this equation has come to be called the deformed Hermitian-Yang-Mills equation. But it's really an extremely different equation. So the deformed, or the Hermitian-Yang-Mills equation for a line bundle is just the Laplace equation, which is linear in particular and always has a solution. This deformed Hermitian-Yang-Mills equation is fully nonlinear and there are algebraic obstructions. So it's really a completely different creature. So this is called the deformed Hermitian-Yang-Mills. Equation. So I'm going to call it just DHYM. Yeah, right. Okay, so these are the equations for objects in the category which should describe realistic particles. So these should be like the stable objects of the category. Yeah. So things that. No, because I have not. Yeah, I'm just saying that if you compute the equations of motion, then these are what you get. So these are somehow describe the particles which should not decay.
So when you say compute the equation of motion, so you mean with respect to some action, or?
Yeah, exactly. So that's what this team does. They write down an action, they compute the variation.
So that the equations of motion will be.
Yeah, exactly. Yeah. So let me just briefly, before I move on, explain the relationship between these two. So now we have this A side and the B side, and by mere symmetry they should be related, right? So let me explain to you how they're supposed to be related. So. Okay, so if you're not familiar with SYZ mirror symmetry, then just take a 3-minute nap. Otherwise, this is okay. So in SYZ mirror symmetry, you have two Calabi-Yau's mirror. If this has so the expectation is that you should have a special Lagrangian torus fibration of x over some base over a base B. And x check should have a fibration over essentially the same base with dual with dual tori. So somehow, I don't know how to draw them, maybe like this. So this is a SYZ mirror symmetry. Okay, so let me explain the relationship between the two objects that I've written down. Well, if I start with a special Lagrangian section of this fibration, so I'm looking at special Lagrangian submanifolds which intersect each special Lagrangian torus in one point. Okay, then under this SYZ mirror transform, these are mapped to holomorphic line bundles on the mirror which solve the deformed Hermitian-Yang-Mills equation. So the holomorphic line bundles with solutions of this equation correspond to sections of this SYZ fibration. So they're sort of simple special Lagrangians in this picture. So for example, if one took a special Lagrangian that somehow looped back, that would correspond to a more complicated object of the derived category on the mirror. So you would expect even an object which was not just a bundle, you would expect it maybe a complex in the derived category. So then you expect to have a Lagrangian which is sort of a section that intersects itself at a bunch of times, and then there's some corrections that come from holomorphic disks wherever the Lagrangians intersect. And so it becomes kind of, again, a complicated story. Yeah, the multiply covering B, yeah. Yeah. Yeah.
And also together something else.
Right, exactly.
On the dual side, you're supposed to get not just an optical Foucault category, but an optical Foucault category together with something else.
Yeah, with
a
sort of best embedding of that submanifold into X. So somehow you should think of so if you take a Lagrangian, let's say. Exactly. I'm looking for a preferred element of the isotopic class. And the same thing here. I'm looking for a metric, a preferred metric, which you can think of as some sort of isotopic class.
So does it mean that you can potentially format some kind of unions of categories, which will be where, say, on the left, the objects will be not Lagrangian sub-isotopic, but just Lagrangian actual?
That's sort of what happens with this SYZ correspondence, that at least for these simple objects, then a metric with a line bundle corresponds to a Lagrangian with an embedding, or a section with a particular embedding. And deforming the metric gives you isotopies of the embedding. So, okay, so that's the relationship between these two problems. Okay, so let me. So I want to focus more on this complex side. So I'm going to try to describe some progress in understanding the existence of solutions to these equations. No, it makes sense in general, yeah. Yeah. And in fact, I'm just about to drop even the assumption that it's coming from a line bundle. I'm just going to work on a compact Kähler manifold with any real 1-1 class. And in some sense, that's natural because if you were to put a B field here, then you can imagine that B field just turns your line bundle into an R class. That's, so if you want to put B fields into the story, then you really need to work with R classes. So I'll just write the equation down and then I'll try to explain that. So remarks. So the first remark is that I'm going to assume that X is Kähler, not necessarily Calabi-Yau, because we also want to be able to consider subvarieties of Calabi-Yaus. And for example, we understand, or at least mirror symmetry makes sense for a large class of Kähler manifolds, not necessarily Calabi-Yau. We want to understand that situation as well. 2, I'm going to assume that I'm going to work just with classes in H11 XR, not necessarily integral. And then I'm going to study the following problem. So when can we solve? So when can we find a representative, let's say alpha tilde, in our fixed cohomology class alpha, such that the imaginary part, e to the minus I theta hat, omega plus I alpha tilde to the n is 0. Okay, so this is the equation that we want to understand. All right. Yeah, exactly. So still 1-1 class, yeah. Just not integral. This could be real. And the reason, okay, so morally the reason, so reason for 1-1, or for R classes, is that if you complexify the Kähler form so that there's a B field, right, then we would be considering, so with a non-zero B field, we would want to solve the equation omega plus I beta plus or minus I beta, depending on your plus square root of minus 1 alpha to the n. Okay, imaginary part. U to the minus I theta hat is 0. But so where alpha now comes from a line bundle, but of course now I can just consider the class alpha plus beta, which is just as good. And then, then that becomes an R class rather than a Z class. So it's really, so one wants to consider not just Z classes. Sorry? Yeah, right, because this is the complex Kähler form. So I just replaced omega with omega plus I beta. And so this becomes omega plus I beta plus alpha. Sorry, there's no brackets around anywhere here. No. Yeah, so the real part is, and then this is the, yeah. So the B field just basically shifts the line bundles. Okay. Well, alpha's, B is fixed, but of course deforming alpha is the same as deforming B plus alpha. They're sort of the same. I can treat them now as one object if I like. Okay, so let me say, so first of all, what is this constant theta hat? So again, it's determined, so let me make this a lemma, but it's totally trivial. If there's a solution of the deformed Hermitian-Yang-Mills equation, let me change notation here just quickly. Let me make that a zeta for a second. Zeta. Okay, so if there exists a solution of this equation, so let me also give this a name. That was DHYM. So if there exists a solution of this equation, then this e to the I zeta is determined by integration. So, and in fact, we have the following. So I should also, okay, so I'm There's a slight lie here because I should also impose here that the real part of this is positive. Omega plus I alpha to the n should be positive. You see, this equation only fixes, I mean, if I multiply this by a -1, it doesn't change the equation. So this just gets rid of that degeneracy. That would swap the sign of the real part. So, so this you can think of as, this is not really an equation. This is just fixing zeta mod 2 pi. That's all it's doing. This follows immediately from this equation, that this is either positive or negative. So, so if we solve this equation, then this constant is topological in the sense that this integral is in C star, and I can write it as an element of some ray. So, okay. So it's the same sort of story that I mentioned for Lagrangians. So I should remark that in general, if you have a class, if you just hand me a class out of the blue, then it can be the case that this integral is just 0, right? In which case this lemma tells you you can't solve the PDE. So the first examples of that occur in dimension 3, but they really do happen. So remark. So if n is bigger than or equal to 3, then this integral can be 0. In which case the equation cannot possibly be solved. So. Okay, so let me recast this deformed Hermitian-Yang-Mills equation so that it's sort of obviously elliptic. So let me rewrite this deformed Hermitian-Yang-Mills equation. So consider the, okay, so this is a slight abuse of notation. The endomorphism of the holomorphic tangent bundle given by erasing an index of this form alpha with using the Kähler metric. So in other words, this is like a j k bar alpha k bar L. Okay. So I shouldn't write this in terms of 1-1 forms. You should turn these into Hermitian forms and then, but okay. So let me abuse the notation for a second. So this is a Hermitian endomorphism with respect to the Kähler metric omega. So in particular, it has real eigenvalues, right? N real eigenvalues. So this has n real eigenvalues, lambda 1 up to lambda n. Eigenvalues, lambda 1 up to lambda n. And then the deformed Hermitian-Yang-Mills equation is the same as the following equation. We can define an operator, theta omega of alpha, which is the sum of the arctans of the lambda i's. And that should be equal to a constant, theta hat, which has to be equal to this topological constant zeta mod 2 pi. So theta hat equals zeta mod 2 pi. Or in other words, e to the I theta hat equals e to the I zeta. Okay, but there's a difference here, right? Which is that zeta we got from integrating is just a point in S1. It's defined only mod 2 pi. The right-hand side of this equation is now a number between minus n pi over 2 and n pi over 2. Right? So this is really, that's why it sort of looks like a silly thing to write, but these objects are really different. This one I get from cohomology is only defined mod 2 pi, and this one, if I can solve the equation, is a sort of a real number. So if you can solve the equation, there's some sort of lift of zeta to R. Yeah.
If
Which one? This one is holomorphic. Yeah. What's the, sorry? Oh, let's say, I don't know, H, JL. Yeah, so I'm basically just using the metric to turn a Hermitian form into an endomorphism. Does that make sense? So you see this operator that appeared when we were discussing graphical special Lagrangians appears again here. So it's the same elliptic operator. Now I'm considering it on complex matrices, but it's got the same. So it's sort of important, and it'll come up later, that theta hat is between minus n pi over 2 and n pi over 2. So in particular, you get strictly more information from solving the equation than you do from cohomology, right? Okay, so let me list a few properties of this operator, which are going to play a role in what I say. So these are just properties of this elliptic operator. So first property I already mentioned. So this operator is valued in minus n pi over 2, n pi over 2. So it's a map from X into this set. 2, regarded as an operator, this is elliptic. So an immediate consequence of this, which let me call 2a, is that if there exists a solution, or if there exists, let's say there exists more than one solution. Yeah. This one. Are you asking about this statement, that it's elliptic? So there's a bunch of different, so you can think of this as a function. Okay, so when I say elliptic here, I mean as a function on Hermitian matrices. And then elliptic just means it's increasing when I move in the direction of the positive cone in the space of Hermitian matrices. That's sort of a meta definition of elliptic. But you can also think of this as a differential operator on functions, for example, if I scale. So I'll write that down a little bit more later. But if you want now, you can just say that if I, okay, so point-wise, this is a function on Hermitian matrices, right? Sum the arctans. If I increase the eigenvalues, then the operator increases. It just means it's that's one way of defining elliptic. Does this make sense? Yeah. Okay. So a consequence of this is that if there exist solutions, alpha 1 and alpha 2, in the same cohomology class, to the deformed Hermitian-Yang-Mills equation with angles theta 1 and theta 2, say, to DHYM, so theta omega of alpha I is some angle theta hat I. So both of these are equal to zeta mod 2 pi. Then, in fact, alpha 1 equals alpha 2, and theta 1 equals theta 2. Theta 1 hat equals theta 2 hat. Okay. So that's a consequence of ellipticity, just the maximum principle. So the point here is that, okay, I remarked here that if you can solve the equation, you get a lift. you might worry that solving the equation gives you a lift, but then there might be more than one if you didn't have uniqueness, right? You could have many solutions of this equation, each giving you different lifts. But this maximum principal argument rules that out. It says if there's a solution, there's a unique lift of this angle. Okay. So the next property is the following. So 3, if this operator, let's see, is in the sort of largest branch, so between n minus 1 pi over 2 and n pi over 2, okay, then actually the form alpha has to be positive or non-negative, right? That's not so hard to see because you see if one of these eigenvalues was negative, then you would have at most n minus 1 pi over 2 coming from the positive eigenvalues and a negative contribution coming from the negative one. So it's kind of trivial, but more generally, if you go down one branch, let's say 4, if this operator is in the next lowest branch, n minus 2 pi over 2, n minus 1 pi over 2, then the operator is bounded below. It might not be positive, or then alpha is bounded below. For some a that depends on the gap between, so this is open, right? Sorry, let me write this slightly more precisely. So it should be between n minus 2 pi over 2 plus delta and n minus 1 pi over 2. Then this is bounded below by a constant that depends on delta. Okay. And that is also not so hard to see because if one of these goes to minus infinity, then you'll get a minus pi over 2 contribution. There are at most n minus 1 pi over 2's left, so that would give you something which is less than or equal to n minus 2 pi over 2. So the lower bound is also easy to see. And lastly, let me, so the level sets consisting of so this is now just like a point-wise statement. So consider the matrices in n by n Hermitian matrices such that the sum of the arctans of the eigenvalues of M let's say are bigger than or equal to theta hat. So these sets are convex. When theta hat is bigger than n minus 2 pi over 2. But they can fail to be convex if you move this down further. Okay, so the two. So the last two properties are going to play a sort of important role in various parts of the discussion. So let me just bring your attention to those two. Okay. Okay, so now I want to discuss a variational approach to understanding the existence of solutions. to this equation. Okay, so this is based on an idea which really goes back to a T-in bot. Say Tia-bot and Donaldson. Which is that if you're trying to understand the existence of solutions to a PDE, which you expect should be related somehow to some notion of stability coming from algebraic geometry, then it can be very beneficial to try to view the equation you're trying to solve as the zero of a moment map for a certain infinite dimensional symplectic manifold. Okay. So try to view the PDE as the zero of an infinite dimensional moment map. And then apply the GIT philosophy, or ideas coming from GIT. This is a really beautiful idea. And it's very powerful, provided you can figure out how to view your PDE as the zero of a moment map. So I'm not going to actually say how to do this here, because the actual moment map framework doesn't really play a huge, at least at the moment, doesn't play a big role in what I'm going to say. But the GIT philosophy will. So I'm going to talk about the sort of GIT part of this statement. Okay, so let me fix some notation. Yep. So I'm just trying to, so so I'm not trying to form a moduli space. All I'm trying to say is that the zeros of the moment map are in one-to-one correspondence with stable points with respect to the, so points in which the sort of weights of the action are positive. So that's the only part of the GIT. Of course, then once you know that, then you can identify the symplectic quotient and the algebraic quotient. So I'm not taking a quotient by a group, yeah. But there is a symplectic manifold that you could try to quotient by the group, which is sort of space of complex structures, and it's acted on by the gauge group. And, yeah. So a similar picture happens for just Yang mills, right, or for Hermitian Yang mills. One can use that to construct moduli spaces. Okay, so let me fix some notation. Okay. So let's fix an element of our cohomology class, which I'm going to write sort of tautologically this way. Then any other representative of this class can be written as any alpha prime in this class is given by, so by the dd bar lemma, alpha prime is equal to alpha plus I dd bar phi, square root of minus 1 I dd bar phi, where phi is a map, phi is just a function on, a real valued function on x, and it's unique up to addition of a constant. Okay, so in particular, after fixing a representative of this class, we can consider the space of all representatives here as just the smooth functions on R. Okay, so let's define space. Okay, so we'll write alpha phi for alpha plus, for this fixed representative plus IDD bar of phi. And I'm not going to worry about the fact that this representation is only unique up to constants for now. Okay, so let's define a space. I'm going to call H, which is going to be the space of smooth functions such that the real part of e to the minus I theta hat, or maybe this should be zeta, let's say e to the I zeta, omega plus I alpha phi to the n is positive. So in the sense that it's a volume form. Okay, so if there's a solution of the equation, right, then it should sit in one of these spaces. Let me write this out a little more in a little more detail. Okay, so what is this? Let's write this out. So this real part of e to the minus I zeta times omega plus I alpha phi to the n. Well, you can write this out as the following thing. So it's equal to function r omega of alpha phi times e to the I. Oh, let me just write out not the real. Let's write out the complex determinant. Okay. Omega plus I alpha phi to the n. So to expand this, you can just choose coordinates where omega is the identity and alpha is diagonal. So you can just expand this in the following way. Like this. Where r omega of alpha phi is the function which just assigns to alpha phi the square root of the product of 1 plus the eigenvalues. Okay, so this is a smooth function, just written in terms of the eigenvalues. This is our elliptic operator from before, and this is the volume form. Okay? So now you can see what this space is. R is clearly positive. This is the volume form coming from the Kähler metric. That's positive. So you can see that this space is just the space of phis such that this operator only oscillates by pi over 2 from zeta, mod 2 pi. Right? So thus, we can write our space H in the following way. So our space H is a disjoint union over elements between minus n pi over 2 and n pi over 2, such that e to the I theta hat is our topological number e to the I zeta. Of the space of functions phi such that the operator theta differs from theta hat by at most pi over 2. Okay? So in other words, right, so this is just saying, this is just saying that theta omega differs from zeta by at most pi over 2, modulo 2 pi. So I just look at all possible lifts of that element, and then I look at the set of objects which differ from pi over 2. This is clearly a disjoint union because every element here is separated by pi over 2, and this oscillation is at most, or 2 pi, this oscillation is at most pi over 2, so they're necessarily disjoint. So then the claim, so you can imagine this is some sort of, okay, so we have this big space of C infinity functions, right? And this is some sort of maybe collection of disjoint subsets. So this is H. Okay, so the claim is the following. Claim is that at most one of these spaces is non-empty. So at most one H, let me call this space H theta hat. So at most one of these spaces, H theta hat, is non-empty. What time do I finish? Now? Tomorrow? 3 hours from now? Okay, maybe I just take a few more minutes and then I finish. Okay, so at most one of these H theta hats is non-empty, and that's just a consequence of the maximum principle using the ellipticity. Okay, so let me now explain the sort of key definition or the key point of these H theta. Oh, so far, no. So the analog here would be that this would be the space of Kähler metrics. So in some sense, the alpha invariants won't appear until we're doing the actual GIT. So right now, I'm just setting up the GIT. Okay, so the key point now is that. Okay, so from now on, I'm going to assume that H theta hat is non-empty for theta hat in this largest range. So this is so I'll try to explain where this enters the analysis and the picture in general, and what are the technical difficulties, or the even more general, sort of the actual difficulties, not just technical, that come when you try to drop this assumption. Okay, so at most one of these is non-empty, and I'm assuming sort of the largest one is non-empty. Okay, so then the key, and this is based on work of Jake Solomon in the symplectic geometry, is that this space H. So I'm going to drop the theta hat. So H is an infinite dimensional Riemannian manifold. So let me just tell you what the Riemannian structure is. Yep. Yep. Oops. So only modulo 2 pi. Yeah, so there's a lifting problem. Yeah, does that make sense? Yeah. Yeah, so somehow the integral only tells you e to the I theta hat, but you really need theta hat as an actual real number. Yeah. So, right, so if you're familiar with the sort of algebraic side, this is like the phase as an element of the Bridgeland stability condition, whereas e to the I theta hat is the thing you get from the central charge. So somehow it's like the, yeah. Okay, so H is an infinite dimensional Riemannian manifold. So how do you do that? Well, if I take a function in this space H, So I just need to tell you what the metric is. So if I take a function in this space H, H is an open subset of the smooth functions. So its tangent space, right, it's just a vector space. So tangent space is just another copy of the smooth functions. So I need to tell you how to take an inner product of smooth functions. And there's a natural way to do that, which is to use this L2 inner product induced by this volume form. Right, and the definition of H is exactly the one which makes this positive. So this is a sort of a legitimate L2 inner product. Okay. All right, so the plan for next time would be to explain how this this gives rise to. So you should imagine that now we have a Riemannian structure. We get a notion of geodesics. You should think of the geodesics as the one-parameter subgroups in the sort of complexified gauge group appearing in GIT, and we'll associate to those weights coming from algebraic geometry. So maybe now is a good time to stop.
Next talk is tomorrow at 4, and of course the style will be here for the whole week. So I'll still return to the question for the sigma invariant. So how do they appear after you set it?
Right, so in dimension 2, right, complex dimension 2, if you're interested in the Kähler-Einstein problem, then you can show that, so essentially the idea is that the alpha invariant allows you to show that your so you can use the alpha invariant to show that the sort of relevant functionals are proper, and that means that you're at a GIT stable point. So that's where they enter there. So here they're not obviously going to enter because the sort of Kempf-Ness functional is not the one that from the Kähler-Einstein problem. So it's kind of a different flavor.